Hey guys, this is three guys, two metals, and two semiconductors. This is titanium crystal structure, and the titanium at room temperature adopts a hexagonal close-packed HCP structure. HCP structure are formed when atoms are packed with AB-AB stacking. This forms a hexagonal structure. The coordination of titanium in its HCP form is 12. You can see that there's 12 1/6 atoms and two 1/2 atoms, plus the three in the middle full atoms, which equals 6.
So the atomic packing factor for titanium we determined to be 0.74, which means that there's 74% of the volume is occupied by atoms inside the unit cell. This was calculated by the APF formula, which takes the volumes of the atoms total over the unit cell volume. Using the coordination number for number of atoms multiplying by the volume of an atom, and then dividing it by our formula, in this case HCP, for the volume of the unit cell. Knowing that H equals 4R radical 2/3, we plug that into our formula, simplify, and solve to find that the APF for titanium comes out to 0.74.
Next, we're going to find the theoretical density of titanium using the formula P equals M over V, where M equals the molar mass times the number of atoms divided by the constant 6.022 times 10 to the 23rd, where the molar mass is 47.867 grams per mole and the number of atoms is 6. This is found is the M equals 4.77 times 10 to the negative 22nd grams. And then using the volume that we found for the hexagonal prism, we can plug in our values, and the density is 4.77 times 10 to the negative 22nd grams over that volume value, plugging in the radius, and that is found to equal 4.5 grams per centimeter cubed. And now you might be asking, how did we find H in that volume formula? Well, first we take half of H, represented by this triangle right here, and we do some trigonometry processes to find what the sides of that would equal. So we found that the sides are H over 2, 2R, and X. So using the Pythagorean theorem, we can find that H over 2 equals 2R times radical 2/3. And then that means that H equals 4R times radical 2/3.
Next, we're going to talk about copper's crystal structure. Copper forms at a face-centered cubic, which is FCC lattice, which contributes to its malleability and conductivity. In the FCC structure, atoms are packed with atoms at each corner of the cube and at the center of each face. FCC structures are packed in ABC order. The coordination of number of atoms for copper. The coordination of number of copper in its FCC structure is 12. The number of atoms in each unit cell is 4.
So now we want to find the atomic packing factor for copper. Using the formula that we used before for APF, which is the volume of the atoms total over the unit cell volume, which is equal to the number of atoms times 4/3 pi r cubed, which is the volume of an atom, divided by A cubed. What is A? A can be found using the Pythagorean theorem in the unit cell to be radical. 2A is equal to 4R. Then plugging into the formula, we get number of atoms times 4/3 pi r cubed divided by 4R over radical 2 cubed. This results in 0.74, which again means that 74% of the atom in the unit cell are occupied.
So now we're going to find the theoretical density of copper. Same formula as before, P equals M over V, with the mass equaling the molar mass times the number of atoms divided by the constant. This time the molar mass is 63.546 grams per mole, and the number of atoms in the FCC structure is 4. So this is the mass equals 4.22 times 10 to the negative 22nd grams. In this case, V equals A cubed because it is a cube, where A is equal to 4 over radical 2R, And then our R for copper is 128 picometers. So the density is 4.22 times 10 to the negative 22nd grams over 4 radical 2 times that number for the radius cubed. And this equals 8.9 grams per centimeter cubed. The derivation for A is much simpler than that of H. As we see, the diagonal in this FCC structure is equal to 4 times the radius. So using the Pythagorean theorem, we can find that 4r squared equals a squared plus a squared, otherwise known as 4r equals a radical 2, where a equals 4r over radical 2, or 2 radical 2r.
Next, we will talk about the crystal structure of the lead telluride semiconductor. The crystal structure of lead telluride is a FCC structure. In this diagram to the right, you can see that the green represents the lead and the red represents the tellurium. Each atom is surrounded by 6 other atoms. Next is our semiconductor B, which is lead tin telluride. The crystal structure for lead tin telluride is also an FCC. It is very similar to the lead telluride structure, where the tellurium bonds in the interstitial sites. In this diagram to the right, you can see that tellurium is represented by green, and the lead or tin is represented by purple.
Next, we're going to talk about the crystalline directional and planar families. For the 120 directional family, there are 24 different directions in this example. They are as listed: 120, 210, 201, 102, 021, 012, 120, -1, -2, -1, 0, -2, -2, -1, 0, and a bunch more. For the graph, we only graphed 6 of the directions, but they were all positive, so it's easier to graph. As you can see here, we graphed 1/2, 1 0, 1/2, 0 1, 1, 1/2 0, 1 0 1/2, 0 1 1/2, and 0 1/2 1. We had to minimize the values so that they could fit in the 1 1 1 dimensions of the cube, and this is what we came up with. For the 1 1 1 planar family, we can see that there are 8 different variations with 1 1 1, -1 1 1, 1 -1 1, 1 1 -1, -1 -1 -1, and so on. For the graph, we graphed 1 1 1 plane. As we see, it is at each corner x equals 1, y equals 1, and z equals 1, and it creates that triangular shaped plane. Now it's time to lock in a little bit. We're going to talk about the linear and the planar densities. The linear density at 210, this is a variation of 120 direction. For titanium, we used the formula for linear density, number of atoms over the length, where we found the number of atoms to equal 1, and the length to equal radical 1.25 times A, where A equals 2R. Using these numbers, we found the linear density to be 3.04 atoms per nanometer. For the linear density of copper, we did a similar method. Using the linear density equals the atoms over the length, we found the number of atoms equals 1, and the length to equal R times radical 10. The linear density for this is 2.47 atoms per nanometer. For lead telluride, we found the length to be the same, because of this FCC also, R times radical 10, where R equals 0.157 nanometers, or the average of lead and telluride atoms. And we found this value to be 4.03 atoms per nanometer. And for lead tin telluride, it was the same process, but with a different radius, including the radius of tin, and we found that value to be 4.24 atoms per nanometer. For the planar density of titanium in the 111 plane, we used the equation planar density equals number of atoms over area, where the number of atoms for this was 6, and the length was equal to 0.2247, and given this, the planar density was 26.7 atoms per nanometer squared. For the FCC structure, we found that the number of atoms that this plane intersects is 2, and the area is represented by 1/2 base times height, given it is a triangle, where we found base to equal radical 2a, and the area equals 1/2 radical 2a times radical 3/2 a. Given this, we can find the planar density of copper at the 111 plane, where the planar density equals 2 over 2 times the radius times 2 radical 3 times the radius again. This gives the planar density equal to 17.6 atoms per nanometer squared. Doing a similar process, we found that the planar density for lead telluride was 23.4 atoms per nanometer squared, and for lead tin telluride, 26 even. And the number of atoms in these structures was 4 for these planes, because they have twice the amount of atoms as the interstitial sites are taken up. Thanks for watching.